So we have finished the charge balance and we have done some preliminary site filling. And so now is the time to fill the remainder of the sites. And this will kind of give you a little bit of an idea of sort of the order of how we do this, and also a little bit more practice with these places where an element gets shoved from one site into the next adjacent site. And in fact, that's the first thing that we are going to take a look at right now. So if you recall, when we did the first part of the site filling, we put silicon in here. Then we needed to put some aluminum in here, but we wanted to be sure that we didn't put all of the aluminum in here. And so just to kind of recap on here, we did this equation where we looked at the total amount of cations that are available for the site. We subtracted out the amount of cations that were already filled up, which in this case was the 7 for silicon, and then we did the sort of insurance policy that we just did a moment ago again with the iron 3+ to ensure that no values for aluminum in this case would be less than 0 or greater than the amount of aluminum present. Okay, and we're going to sort of redo this same sort of calculation a little further on as we begin to move other ions into, or other cations into different sites. So let's start off with the aluminum that goes into the octahedral site, into the six coordinated metal site. Well, there is no other place where aluminum can go. And so here we can very simply just say, well, the aluminum that is going into this site is just equal to the total amount of aluminum that we have available. So it'll be the normalization factor. Again, I'll put the $ in front here, okay, times the amount of aluminum that we have, which is right here, okay? But we have to subtract out the aluminum that we've already used over here. We can't reuse some of that aluminum, so minus the aluminum that's already been used. And so we have 1 mole of aluminum here in the tetrahedral site, and we have 1 mole of aluminum here in the 6 coordinated metal site. And again, because this is built off of this, the values that I've selected for the weight percents of the different elements are based off of the actual n-member formula here. You can see that I do indeed have 1 aluminum in this site, and I do indeed have 1 aluminum in this site. So let's continue on here. Well, titanium, this is by and large the only site in an amphibole that titanium will probably go in. There are rare occasions when it might go into another site, but in general it's going to be here in the 6 coordinated metal site. So we can simply just say that this is going to be the normalization factor. Again, I'll put my $ in there, times the amount of titanium. Okay, so iron 3+, again, this will be the only site probably that iron 3+ will go in. There may be some rare occasions where, for example, you might want to put an iron 3 column here in the tetrahedral site. But in general, I think for the simplified version here, we're just going to assume that all of the iron 3+ is going to be in the 6 coordinated metal site. And so we need to put that in here. Now, we don't need to use the normalization factor times some iron number because we conveniently already calculated normalized iron 3+, and because this is the only place where it's going to go, we just have to click on that and it is already set up for us. And again, in this case, because there is no iron in this amphibole, the value is 0. But again, we'll see later on for these other amphiboles that some iron will show up. Okay, so now we have the issue of iron 2+ and magnesium 2+. And here's where it gets a little bit complicated because there are a couple of different things that are going on here. One is that both of these cations, iron 2 and magnesium, can go into the 6 coordinated site and, as you can see, can go into the 8-coordinated site as well. So they would make an amphibole akin to something like gedrite or cummingtonite or anthophyllite or grunerite. Okay, a variety of possibilities there. So we've got to figure out a way of being able to put some iron and magnesium into the 6-coordinated site, and then some iron and magnesium into the 8-coordinated site. But we have the added complication here that we have two different cations that we have to do this distribution with. And so we've got to kind of make up our mind how we are going to distribute them, because since Excel is entirely mathematical based, we really have to come up with some mathematical formula to permit us to do this. We can't just say, well, in some cases we're going to have it be one way, and in some cases we're going to have it be a different way. We have to have some formula that's going to make this decision for us. And what I'm going to do here is I'm going to make the assumption that we are going to put iron into the 6-coordinated site before we put magnesium into the 6-coordinated site. And so I'm going to try to put all of the iron in here first, and then I am going to, whatever space we have left over, I'll put magnesium in, and then essentially move leftovers into the 6-coordinated site. Now, I don't know if I necessarily have a good justification for this. I think you could probably argue that, well, you could put magnesium in first and then fill the remaining space with iron, and then move iron over into the next site. The way you want to think about this is based a little bit on sort of the structural chemistry of these minerals and the cation sizes and crystal field effects and a kind of a variety of different sort of structural things that I think are beyond the scope of this tutorial here. So I'm just going to kind of make this arbitrary decision that I'm going to put iron in there first, simply because I have the column here first. But if you are really keen on knowing sort of what is more likely, then you'll probably want to read up a little bit more on amphibole structural chemistry. But keep in mind that this is only a mathematical sort of estimation, and that there probably really is iron and magnesium distributed. There would be iron and magnesium distributed between both sites, and you really need for example, a single crystal structural analysis in order to really know what that is. And so we can play all the little mathematical games that we want, but it is only a model for what nature is giving us, and not necessarily the absolute answer. But in any case, let's take a look at how this is set up. So there's always the slight possibility, I suppose, that we may have already filled this amphibole up. So the way that I'm going to set this up is we're going to go equals, and then we're going to do a formula that says, well, what is the total occupancy of this site? And the total occupancy is 5, okay? And then we are going to subtract out the things that absolutely already have to be in the site. And the things that already have to be in the site are the 3 things that we've already put in there, okay? And so I'm going to go that it's going to be aluminum, and it's going to be titanium, and it's going to be, if I can get in there, it's going to be iron 3+, okay? So those are the absolute things that have to be in there, okay? And I will hit return, and okay. So you see that we have this number 4 here, which is, or this 4.0, which is completely meaningless because we don't even have any iron in this amphibole. So clearly we've got to do some additional things to this formula, okay? And what we're going to do is we're going to do the same thing that we've done here with aluminum. We're going to do this check to make sure that a value isn't less than 0, which clearly isn't in this case, but also that a value isn't greater than the amount of iron that we have. Well, here, obviously, we see that this value is indeed greater than the amount of iron that we have, so we need to fix that. So I'm going to start off again by putting the if statement in front, and then we're going to do the test to make sure, first of all, that it's not less than 0. So again, we do if it's less than 0, we want the value to be 0. Okay, then we are going to test it with if, we're going to put another if statement in here, and then we want to make sure that if this entire equation here at the beginning, if this is greater than the amount of iron 2 that we have, well, where is the amount of iron 2 that we have? Conveniently, that is this normalized iron 2 value that we've calculated. So again, we don't need to worry about multiplying anything by a normalization factor. It's already taken care of for us. So if it's greater than the amount of iron 2, then we just want it to be the value of iron 2. Okay, so if it's greater than that, it can't exceed this number, so all it can be is that number. And if neither of those two scenarios are come to pass, if it's neither less than 0 or neither greater than the amount of iron 2 that we have, then we can just take this original formula and assume that that will be the default. And again, we need 1, 2 parentheses to close this out. And so now you see that we actually get 0 because that represents the fact that we really never had any iron to start with, and so that has to be 0. Okay, so it turns out that the formula for magnesium is essentially identical to that. We're going to do it the same way. And now, rather than sort of write that whole thing out again, I'm going to actually do this in a somewhat easier way. I'm going to just copy this whole formula. Okay, and then I'm going to paste it in here, and then I'm just going to make some changes. Okay, so right now, I'm going to hit return here. So right now, these two formulas are identical. Okay, but I'm going to need to make some changes in order to have this be adaptive for magnesium. So again, for magnesium, we want to have it, we want the formula to represent the amount of material that is available in the site, which is still 5, minus the things that have to be in there. Well, the aluminum, titanium, and iron 3 that we previously calculated have to be in there, but now this iron 2 that we've also calculated also has to be in there, and so I'm going to add that iron 2 cell to the formula as well. And because we see that this little cluster here, 5 minus AP8 plus AQ8 plus AR8 plus AS8 is here, we want to actually reproduce that same cluster in all of the places where it shows up. So it's going to be here, here, and here. So there are all the places, okay? And now we do have to make one additional adjustment, because right in here it says if if 5 minus all the things that have to be in the 6 coordinated site is greater than iron 2, well, we're not looking at iron 2 anymore. Now we're looking at magnesium. And so this number has to change from AI8 to the normalization factor times the magnesium number. Okay, and then this normalization factor times the magnesium number also has to go in this place as well. Okay, so now this equation has been converted from the iron 2 version to the magnesium 2 version. Okay, and here we get our 4 magnesium, and indeed, if we look back at the original N-member formula for CaTO4 right here, we see we do indeed have the 4 magnesiums. Okay? So now here we can just sum up the 6 coordinated cations. So I'm just going to add all these up, and hopefully we get the 5 that we expect. And we do. Okay, so now we have the 8 coordinated site to worry about, and so the question is how much iron 2 plus is going to be in this site and how much magnesium is going to be in this site. Well, in this case it's pretty easy because there is no other site. There's no larger site for those ions to go in, and so this is just going to represent the total amount of iron 2 that we had minus the amount that we used over here, and this is going to represent the total amount of magnesium that we have available minus the amount that we used over here. And so I'm just going to set those up. So this is going to be the total amount of iron 2, which again we get from here, minus the amount of iron 2 we've already used, which is there. And again, because there's no iron in this amphibole, it comes out to be 0. The magnesium is similarly calculated. We look at the total amount of magnesium that we have, which is the normalization factor. And I'll put the $sign in there. You can see I've been a little inconsistent with whether I've been using the $sign or not. That's probably not very good, so I may go back later on after I finish the video and sort of fill out all the $signs where I want them. Times the total, or the raw magnesium. So that's the total amount of magnesium that's available, but we want to subtract out the magnesium that we've already used right here. And so as you can see, we've used up all of our magnesium already, so none of it is going to show up. Okay. Now we move on to our next cell. Well, calcium, there is no other place for calcium to go. There is a rare amphibole that does actually have calcium in the A site, but it's quite uncommon. It's not something I think that you generally have to worry about in your natural analyses. And so I think it's safe to just assume that all calcium will be in the 8 coordinated site. So again, we will do calcium, which will be the normalization factor, times the amount of calcium. Okay. And now we are going to take a look at sodium. Now keep in mind again that sodium can be distributed between 2 sites. And so we have to do the same little game here with sodium that we did with iron and magnesium. Okay. And so I am going to sort of do the same thing again. Now, there are 2 ways that you could do it. I could just copy this formula from over here and just replace everything. That's probably the easiest way to do it, but instead I'm going to kind of build this up from scratch again. So I'm going to go equals if, okay, and now we're going to look at what's the total occupancy of the 8 coordinated site. Well, if we look over here, we'll see the total occupancy is 2. So we do 2 minus the amount of material that's already used up in here. And so what is used up in here already? Well, there's going to be the calcium that we've already put in there, and then whatever magnesium we may have put in there, and whatever iron 2 plus we may have put in there. So those are the things that absolutely have to be in that site. Okay. Again, we want to make sure that if this number is less than 0, that we just replace it with a value of 0. Alternatively, if this number is greater than the amount of sodium that's present, so let's copy this again, copy, paste. And now if this is greater than the amount of sodium present, and we do it the same way, we do the normalization factor times sodium number. Okay, and if it's greater than the amount of sodium, well, we can't, again, have it be any bigger than the total amount of sodium that's present. So I'm going to put that in here. And then lastly, if neither of those 2 limitations are exceeded, then we just want what's in the middle. And that will be that. And that will finish it off. And again, we need 2 parentheses to close the whole thing off. And there we get 1 sodium showing up. Okay, and again, if we look at the formula for catophorite, that this is in line with how our catophorite was put together. So we see we have 1 sodium and 1 calcium in the 8 coordinated site, and indeed we have 1 sodium and 1 calcium in the 8 coordinated site. And again, I'm going to add all of these up. And as you can see, it should add up to 2, which is, exactly what it should do. So we have our final site fillings here. Okay, so let's finish this up. So you can see that we put some sodium in here, and so we're going to ultimately move some sodium into here. And so this is going to be equal to, again, the total amount of sodium that potentially we have available to us, the normalization factor, okay, times the amount of sodium. There we go, minus the sodium that we've already used. Okay, and here is the sodium that we've already used. Okay, so for potassium, this is the only site that potassium can go in. So I'm going to just do the normalization factor times potassium. And again, I'll put that $sign here in front of the normalization factor. And again, we had no potassium in our original analysis, and so potassium shows up here as 0. Now there's one kind of additional column that I'm going to add here. I don't have it in here at the moment, but you can see if you look back at the original amphibole formulas that a number of these have a vacancy in the large 12 coordinated site. And so it might be convenient to sort of maintain a record of this vacancy. And so I will add an additional column here. And I will just kind of call it vacancy. And it will be the in the A site. Okay? And how do we calculate this vacancy? Well, it's essentially just 1, because the maximum filling of the site is 1. So it's going to be 1 minus the amount of sodium and potassium that we have. So it's just going to be equal to 1 minus sodium and potassium. Okay, now again, there's always that slight chance that, let's say that sodium comes out to be, say, 1.01 or 1.02. Again, analytical error. We would end up calculating a negative number here for the vacancy, and we, again, don't want to do that. And so we're going to have just a simplified if statement here, and it's really just going to be if this number is less than 0, then 0. Otherwise, we just want it to be what we originally assumed it was. And this doesn't have to be a complicated if statement. There is no number of vacancies that we can exceed, so we don't have to put that part of the equation in. And so this is just a simplified version to ensure that we don't get a negative number there. And then we can add these together. And now you see we have our 1 for our A site, and this will always be 1, or generally always be 1, because this vacancy number will nominally vary between 0 and 1. And so as we add all 3 of these columns up together, this will be 1, or on rare occasion it might be a little bit over 1. Okay, so we have completed the site fillings for the anions already, and so all of our site fillings are done. So at this point, we could even name the amphibole, but I'm going to take a little pause here, and then we will actually move on to the oxide calculation, which is what you would report if you were putting this data into a paper, for example. Okay.